In this lesson, we're going to look at the graphs of a few trigonometric functions, mainly periodic ones. We can just have a look at this link first to see where we're going. So this is what these three graphs are going to look like. Okay, so you can play around with this app to see how we get to those three graphs. Okay, two things to note about trigonometric functions. Okay, there's a period, which is how long it takes for it to complete a full cycle, and the amplitude, which is basically how big it's going in a vertical direction. Okay, we'll draw a graph and then have a look at those two things. So what we want to do is produce a graph of cosine x, okay, essentially to see how the value of cosine x, which will be in the vertical axis, changes as our angle changes. So in order to do this, I'll start with an angle of 0. So I'm at this angle of 0. What's my cosine value? It's the x-coordinate on this unit circle diagram. It starts at 1. Okay, so I'll mark that as cosine of 0. And then essentially we'll go around this unit circle to pi on 6, pi on 4, pi on 3, etc. and mark these points in the corresponding angle. So cosine of pi on 6 is root 3 on 2. Go to your calculator, it's like 0.866. So I can mark it probably about here somewhere. And keep going around. Root 2 on 2, or 1 on root 2, I think it's 0.707. But I don't have that marked on my diagram, so I'll just look at root 3 on 2, which is a half. Mark this in here. And then pi on 2, cosine value is 0. Okay, so that's the idea. And then it should be able to have some graph of what this relationship looks like, how the cosine value changes as the angle changes. When we're using radians, we always use x for the angle. So go ahead and plot the rest of those points, all these points plotted, and then we can join it with a smooth curve. Okay, that's what my curve should look like. Obviously we've got a lot of nice symmetry around there, just like in our unit circle. What about some of these angles? Minus pi on 6? Well, all that means is pi on 6 in the opposite direction on the unit circle. Okay, so we'll get these same sort of relationships happening. So that's what cosine x looks like. So now we can talk about things like the period and amplitude of the function. Period of the function, how long does it take to repeat itself? Well, these 2 points are corresponding points on the same cycle in the end of the cycle, because this will just keep doing the same thing over time. All I really need to know is what's that distance? Well, from 0 to 2 pi, that's 2 pi. Would be the period. What's the amplitude of the function? Okay, so amplitude is how much it deviates from its average value. So the average value of this function is the x-axis. It deviates a distance of 1 from the x-axis. Okay, alternatively, I could think of what's the maximum value is 1, what's the minimum value minus 1, and find the distance between them. So the distance between these two is 2, and then divide it in half to get 1. Okay, but essentially this is my amplitude, which would be 1. Okay, so what I wrote up there isn't exactly correct. It should be calculating half the distance between min and max. So why is the amplitude important? If you think if I have a weight attached to some spring and I've got it bouncing up and down, okay, it might get to here at its highest point and then down to here at its lowest point. We're just interested in how much it deviates from that average value so we can determine things about the spring. That's one of the reasons why we'd want to do that. Okay, and let's see if we can do this. Use the graph to find the values of x which satisfy cosine x equals 0.5 over this domain. All right, so I'm looking for what angle x has a cosine of 0.5. So I could find where 0.5 is and draw a horizontal line. Okay, the line y equals 0.5. And I can read off these values, these angles that have a cosine of 0.5. Okay, between the domain 0 to 2 pi. So I'm not going to include this one because it's outside the domain. But my values would be pi on 3 and 5 pi on 3. Okay, those two angles have a cosine of 0.5. We'll look at ways to solve those algebraically in the future. Okay, today is more just about period and amplitude. Now do the same thing for sine. Okay, graphing sine x. This time we're using the y coordinates of these angles all the way around. So I'm really focusing on all of these points and plotting approximations of these numbers just like I did for cosine. Sine x looks like, and then I can continue that into the negative as well, either using the unit circle diagram or just by following the pattern of this graph. Yeah, that's sine x. What's the period of the function? Well, here are 2 points that correspond, and they are exactly 2 pi away from each other. So the period would be 2 pi. What's the amplitude? Well, again, my average value is the x-axis. This distance between them is 1 unit. Okay, and the final one, sort of looking forward, use the graph to find the values of x which satisfies sine x equals -1 over this domain. So I'll find where -1 is and draw my horizontal line. And looking for angles x which have a sine value of -1. So I've got this value and this value. I'm only looking for values between 0 and 2 pi. So I'll exclude this value since it's outside the domain. And all I have is an x value of 3 pi on 2. All good. We can also graph tan x. You probably won't see much of tan x after this lesson just because it's not that useful for modeling, but we can still graph it. Just remember that tan is the y coordinate divided by the x coordinate. So for example, at 0 radians, I'll do 0 divided by 1, which will give me 0, and I'll mark that point here. At pi on 6, I'll have to do a half divided by root 3 on 2, which is about 0.58. For pi on 3, it'll be the y coordinate divided by the x coordinate, 1.73. And for pi on 2, it'll be 1 divided by 0, which is undefined. So when I start to mark these on my graph, it gets a little bit interesting. I'll mark these first few, so 0.58 is about there, 1.73 about there, and then this one that's undefined, whenever there's a point that's undefined, I'll put a dotted line all the way through it because there'll be an asymptote through there. So I'll go ahead and plot points for all these other ones as well. You won't need to divide all of these because they'll be the same values, just negatives of them. So for example, here will be minus 0.58. Here will be minus 1.73. And remember, these ones, since we're in the quadrant where tan is positive, will be the same value but positive. So we'll go ahead and plot all of these points and then have a look at what the graph looks like. Like if I was to connect these, essentially as we get closer and closer to pi on 2 or 90 degrees, the tan value gets bigger and bigger. So it sort of asymptotes up like that. So this is what tan looks like. And I can do the same thing with some negative values out here as well. With another asymptote. So it looks completely different to sine and cosine, and you'll probably never see it again, but it's good just to know what it looks like. All right, what's the period of the function? So between these 2 points is a new cycle, but there's only pi between them, so the period's only pi. What's the amplitude of this function? Well, it sort of goes off into infinity, so it's really like not applicable. And use the graph to find the values which satisfy tan x equals 1 over the domain 0 to 2 pi. So I'll draw my line at y equals 1, and I've got whatever these angles are. Okay, there's 2 of them where it equals 1, and on a graph you could just read off some approximations, but what you'll find out later is that the first one is pi on 4, okay, exactly halfway between pi and pi on 2, and the third one, the second one, since it's still in that domain, is 5 pi on 4. Okay, so these 2 angles are literally, there's pi on 4, and down here there's 5 pi on 4. Okay, both angles that have pi on 4 between here. Okay, but you just read them off. Alright, from here have a go at that problem, and for homework is to just look at sine and cosine, look at the unit circle, and just reflect on the relationships between them and the symmetry that exists around there.